we are moving into the next important result of finding variance of sum of random variables. Next definition, that is let x1 xn be a n random variables having finite variances. Then one can define variance of sum of random variables from I is equal to 1 to n. Let x1, x2, xn be a n random variables having a finite variances. That means first and second order moment exist and it is finite. Then we are defining the variance of sum of random variable. That is going to be individual variance plus the double summation over covariance between any two random variables provided I and j is not equal. That is a variance of sum of random variable is the variance of individual random variable with the summation plus covariance of any two distinct random variable. That is going to be the variance of sum of random variable. This can be rewritten. That is summation of I is equal to 1 to n variance of each random variable. Since using the result number 2, covariance of x comma y, that is same as covariance of y comma x. That means the second summation can be rewritten in the form of 2 times double summation covariance of xi with xj. Now the condition is instead of I is not equal to j, I can write I is less than j because we have put the 2 times. So both the statements are one and the same. Here also we can go for one special case. Suppose xi's are independent random variables. Independent, when I say independent random variables, that means they are mutually independent random variables. In that case, we can use the previous result, that is result number 5. When any two random variables are independent, then the covariance is going to be 0. Therefore, the second the summation whole thing it won't come. Therefore, variance of sum of random variables is same as sum of variance of individual random variables when xi's are mutually independent random variables. Now we will give the definition of a expected value of a random vector. We have already given the definition of a expected value of function of a random vector. Now we are going to give the definition of a expected value of a random vector. Let x1, x2, xn be a n dimensional random variables the expected value of let me denote this random vector in the form of capital X. Let me denote x1, x2, xn random vector with the notation capital X. So, I am going to define the expected value of the random vector capital X, which is denoted by expectation of X is defined as expectation of X is nothing but, since x1, x2, xn's are vector, the expected value of X is also going to be vector whose elements are expectation of x1, expectation of x2 and so on, expectation of xn. We are finding the expected value of a random vector. Therefore, that is also going to be a vector whose elements are expected value of individual random variables, provided the expectation of Xi's exist for I is equal to 1 to n. So, as long as a individual expectation exists, one can define expected value of a random vector with the elements is x1, x2, xn. In the same way, we are going to create a matrix whose elements are variance and the covariance between any two random variable. That is the next definition. The next definition is covariance variance matrix. Let capital X, it is a random vector for the random variables x1, x2 and so on, xn be a random vector. Either you can say random vector or n dimensional random variables or random vector with n random variables, such that the expectation of xi square, that is a finite for the random variable 1, 2 so on till n, as long as the second order moments exist, one can go for defining a covariance variance matrix. Then the covariance variance matrix, that is denoted by, in the big summation notation of the random variable capital X, that is defined as, it is in the big summation notation, it is a matrix whose elements are the first element is variance of x1 and the first row second element it is a covariance of x1 and x2, like that so on. The first row the last element, that is a covariance of x1 with xn. Now coming to the second row. Second row is covariance of x2 with x1. second row second element, that is a diagonal element, that is variance of x2. Like that you can keep writing. The last element in the second row, that is covariance of x2 with xn. Like that you can fill up the last row with the first column, that is xn with x1. The last row second column, that is covariance of xn with x2, so on. The last row last element, that is a diagonal element, that is variance of xn. So, this matrix is n cross n order. We are creating a covariance variance matrix for n dimensional random variable. Therefore, this matrix is always n cross n, whose diagonal elements are covariance of individual random variables, and the other elements are covariance of xi with xj for the ith row and jth column. By using the property of covariance of x comma y is same as covariance of y comma x, you can conclude that this matrix is a symmetric matrix. All the diagonal elements are the variance, that is nothing but covariance of xi's with the xi's. Therefore, it is becomes a variance of xi's. So, this matrix has the very important property, that is the matrix is positive semi definite. That means for any a1 comma a2 and so on an belonging to Rn, the vector, suppose I denote this as the vector A, suppose I denote this as the vector A whose elements are a1, a2, an belonging to Rn, A vector multiplied by the matrix, then A vector transpose, this value is always going to be greater than or equal to 0. That is called the matrix is a positive semi-definite. The covariance variance matrix of random vector is always positive semi-definite. We will give a one simple example how to compute the expected value of a random vector and covariance variance matrix. Example, let capital X is the vector whose elements are x1 comma x2 be a random vector with joint probability density function is given by, that means both the random variable x1 and x2 are continuous type random variable. Therefore, we are defining the joint probability density function of x1 comma x2, that is 1 divided by x1 when x1 takes a value 0 to 1, whereas x2 takes the value 0 to x1, 0 otherwise. So, this is the joint probability density function of the random vector x1 comma x2. We can verify double integration of a joint probability density function has to be 1. Let us find expectation of x1, then we will go for finding expectation of x2, then we can go for finding expectation of x1 square, then we can go for expectation of x2 square, then we can go for expectation of x1 x2, then we can go for expected value of the vector x. We can find out what is the covariance variance matrix, then we can go for verifying whether it satisfies A summation A transpose is greater than or equal to 0. The last one is the verify A times matrix A transpose is greater than or equal to 0. So all those things you can do one by one. First start with the expectation of x1. Expectation of x1, you can find the probability density function of x1 from the joint probability density function, then you can go for the expectation, or you can use the first definition, that is a expected value of function of a random vector. So we are going to use that is same as integration from 0 to 1, integration from x2 to 1, x1 1 divided by x1 dx1 dx2. You see that the joint probability density function is 1 divided by x1, where x1 is range from 0 to 1, whereas x2 range is 0 to x1. Therefore, expectation of x1 is double integration 0 to 1 x2 to 1 x1 times 1 divided by x1. 1 divided by x1 is a joint probability density function of x1 x2. If you do the simplification, you will get the answer 1 by 2. Similarly, you can go for finding expectation of x2, that is integration 0 to 1 0 to x1 x2 times the joint probability density function integration with respect to x2 integration with respect to x1. Again I am using the expected value of function of a random vector. This is same as 1 divided by 4. Similarly, we can go for expectation of x1 square, that is same as same method what I have done it for expectation of x1, that is integration 0 to 1 integration x2 to 1 x1 square, the joint probability density function is 1 divided by x1 dx1 dx2. Or you can use the change of integration and you can change the order of integration, still you can go for it and you can get the answer, that is 1 by 3. Similarly, you can go for expectation of x2 square, that is again 0 to 1 0 to x1 x2 square 1 divided by x1 dx2 dx1. I am using the same definition again, that is same as 1 divided by 9. So till now we have got expectation of x1, expectation of x2, expectation of x1 square, expectation of x2 square. Now we will go for finding expectation of x1, x2. The same technique, that is expectation of x1, x2, that is same as integration 0 to 1, integration 0 to x1, x1, x2 multiplied by the joint probability density function dx2 dx1. If you do the simplification, you will get the answer, that is 1 by 6. So now we are going for the next result, that is expectation of a random vector. That is a vector whose elements are expectation of x1 comma expectation of x2, this vector. That is same as, already we got the result, expectation of x1 is 1 by 2, expectation of x2 is 1 by 4. Therefore, this vector is 1 by 2 comma 1 by 4. The next is finding the covariance variance matrix. Since we have only two random variables, it is going to be 2 cross 2, whose elements are variance of x1, covariance of x1 with x2, covariance of x2 with x1 or x1 with x2, both are one and the same, and variance of x2. That is same as, we got the expectation of x1 and expectation of x1 square. So the variance is expectation of x1 square minus expectation of x1 whole square. So if you do the simplification, you will get the answer 1 by 12. To find the covariance of x1 x2, you need expectation of x1 x2 and expectation of x1 and expectation of x2. So all three we got it. So substitute the values, that is 1 by 6 minus 1 by 2 into 1 by 4. So you simplify, you will get the answer, that is 1 by 24. Since covariance of x1 x2 is 1 by 24, that is again a covariance of x2 comma x1, that is same as covariance of x1 comma x2, that is 1 divided by 24. Variance of x2 is expectation of x2 square minus expectation of x2 the whole square. So you do the simplification, you will get 7 divided by 144. So this is the covariance variance matrix for the random vector x1 x2. Now we are going to verify whether this covariance variance matrix satisfies the condition A covariance variance matrix A transpose going to be greater than or equal to 0. Let's compute. So here we will go for A with the two elements A1 comma A2 and the matrix transpose, that is A1 A2. So substitute the, that is A1 comma A2 and the matrix value is 1 by 12, 1 by 24, 1 by 24, 7 divided by 144 multiplied by A1 A2 transpose vector. Do the simplification. Do the simplification. First you will get 1 by 12 A1 square plus A1 A2 plus 1 by 4 A2 square minus 1 by 4 A2 square plus 7 by 12 A2 square, and this is same as 1 by 12 A1 plus A2 divided by 2 whole square plus 1 by 36 A2 square, which is greater than or equal to 0. Therefore, we are concluding this particular covariance variance matrix also positive semi definite.